Okay, so here we are, lesson 2 in our brief unit on quantum mechanics. Today, we're talking a little bit more about some of the background. The last lesson we looked at the photoelectric effect, and we looked at kind of Planck's contribution and his kind of quantum idea. Today, we're looking at the contributions of another two scientists, Arthur Compton and Louis de Broglie, and we're going to take a look at what they've done, and this is going to wrap up kind of the historical things that we're going to look at because this really sets the foundation. So in your textbook, these are the page references, and I would say, at the end of this lesson, these are the essential learnings that really, or are really the learning goals that we want to get out. We want to recognize that the momentum of a photon is given by P is equal to h over lambda, or hf over c, and we're going to show why. We're going to investigate the Compton effect, where electrons are ejected from the surface of a metal when X-ray photons strike that metal. It's an example of the conservation of energy and the conservation of momentum. So it's similar to the photoelectric effect, but it's kind of, it includes momentum now. We're also going to look at de Broglie and how he hypothesized that matter has particle-like properties and wave-like properties. And this is a huge, huge, huge quantum idea, is that matter has properties like waves, which really hadn't been thought of. And we'll talk a little bit more about that. And that really we can quantify a wavelength of matter. It's called the de Broglie wavelength. And that's given by lambda is equal to h over p. So first, let's turn our attention to the Compton effect. Arthur Holly Compton, this is back in the 20s, performed a series of different experiments involving the photoelectric effect. Okay, so this is very closely tied to that. He directed high energy X-rays with a known frequency at a thin metal foil. Okay, so he had some high energy X-rays that came in, and what he noticed, just like the photoelectric effect, he noticed that there were some electrons that were kicked out of the metal, okay, but he also noticed that some lower energy photons were emitted. And this is what we call scattering. So the emitted photons, as it turns out, are simply the original X-rays that are deflected because of their collision with the electron. Okay, and that's what we call scattering. And this effect is called the Compton effect. So this is what Compton hypothesized. He proposed that the energy of the initial X-ray is equal to the energy of the final X-ray plus the energy of the electron, right? And this is the conservation of energy, just like we saw in the photoelectric effect. And because we had been able to quantify the energy of a photon, so here's an X-ray photon, we know that its energy is equal to h times its frequency, then we have a way now of being able to express these energies. But he also said that the momentum would also be conserved. And so this is another thing that he said. Momentum of the initial X-ray would be equal to the momentum of the final X-ray plus the momentum of the electron. But the question then became, well, what's the momentum of a photon? It doesn't have any mass, and it travels at the speed of light in a vacuum. So how can we quantify the momentum of an X-ray? But around the same time, of course, Einstein suggested that mass was another form of energy. So we kind of saw in the special relativity part of this unit, or we will see depending on where it is, Einstein predicted that E is equal to mc squared, and that any decrease in mass of a system would show up in an increase in the energy. Okay, so what that means is if we rearrange this, we have a different way of thinking about mass. And as it turns out, this is going to be really, really important, because what this allowed Compton to do was to find a way of describing the momentum of an X-ray. So let's take a look at a really simple and quick derivation, and this is what Compton was able to do. So first of all, we're going to start with our classical definition. Momentum is equal to mass times velocity. Okay, but now we're going to use Einstein's result, and we're going to say, well, wait a second, mass is equal to E divided by C squared. Okay, so we've simply taken this formula and we've put it here. Okay, so if we simplify this, we get that momentum is equal to E over C, so energy divided by the speed of light. Okay, now that's not all there is to the story. Let's also remember that the universal wave equation tells us that V is equal to F lambda. So because we're talking about light, C is the speed of light, and that's equal to F lambda. So C is equal to F lambda. And further to that, we can say that, okay, well, momentum then is equal to, instead of E over C, we can say it's equal to E over F times lambda, because we've simply taken this result and we've put it here. But because this is quantum, and because of Planck's idea that energy is quantized and that the energy of a photon is h times f, then we can replace this and we arrive at P is equal to h over lambda. So here's a way of expressing the momentum of a photon in terms of its wavelength and Planck's constant. And so Compton's work showed that photons do collide and exchange energy with particles according to the law of conservation of energy. They have momentum, and that their momentum is conserved during those collisions as well. And so this idea of Compton's kind of lent support to the idea that light is a wave and a particle. It has wave-like properties and particle-like properties. And in 1927, Compton won the Nobel Prize for this work. So let's take a look at a couple of examples of the Compton effect. So this is the example one: a 25 electron volt X-ray photon collides with an electron. I'm going to alter this question just for a moment, and I'm going to say, what's the momentum and the wavelength of the original photon? So the first thing that we have to know is that we're given an energy. This is a 25 electron volt X-ray. And I know we're still probably getting used to the idea of these units. Electron volts are a unit of energy, so there's that. What's the momentum of the original photon? So if we're starting to think about this, we have an energy, we need to turn it into a momentum. So we've got, remember that momentum is equal to E over C. Now there's a couple different ways of getting to the answer, but this is the most direct. And so we're going to work with this. So first of all, we've got energy, and we need to turn this electron volts into joules. And so there it is. So 25 electron volts times our conversion factor gives us 4 times 10 to the negative 18 joules. Okay. So now let's find the momentum. Momentum is equal to E over C. And if we do this division, we find right away that the momentum is equal to 1.3 times 10 to the negative 26 kilogram meters per second. Now, because the units of momentum, they don't have a derived unit, it's just kilogram meters per second. But you can see that this is one of the reasons we needed to change that electron volts into joules, because we have to be working in SI units if we want our units to work out. Okay, so we've got the momentum of the original photon. Now let's look at finding the wavelength. We know that P is equal to h over lambda. Okay, so we're well on our way. If we rearrange this equation, the wavelength is equal to h divided by the momentum, and we do our calculation because we know h, it's a constant, and we arrive with 4.97 times 10 to the negative 8, which, correcting for sig figs, is 5.0 times 10 to the negative 8 meters. And there's the wavelength. So that's a straightforward example to kind of get us used to photon momentum. All right, so now let's look at an example of the Compton effect. Okay, so this is example 2 that we're going to do now. An 85 electron volt X-ray collides with an electron. The resultant photon is deflected 60 degrees from the original line of travel and has a wavelength of 214 nanometers. We want to find the momentum of the original photon and the deflected photon. So there's 2 things that we have to do for part A. And in part B, find the energy that's given to an electron and calculate the speed. So the first thing we need to do, as we saw in the previous example, is this 85 electron volts. We need to turn that into joules. And here we've done it with our conversion, 1.36 times 10 to the negative 17 joules. And so now let's begin with part A. We need to find the momentum of the original and the deflected photon. So we're going to start with the original photon. And again, we have an energy. So the simplest way to do this is to say that the momentum of the initial photon is equal to E over C. This is a straightforward calculation. We take our energy, 1.36 times 10 to the negative 17, we divide it by the speed of light, and we get the momentum of our initial photon. Okay. Now we have the momentum of the deflected electron, the deflected photon. This one, although we weren't given the energy, we were given the wavelength of the deflected photon, and that's just as valuable because we can say that P is equal to h over lambda, and we can do this calculation and we can see that the deflected photon has a wavelength, it has a momentum of 3.1 times 10 to the negative 27 kilogram meters per second. So there's part A finished. We found the 2 momentums. Now we want to do part B. Find the energy that's given to the electron and calculate its speed. So we're going to investigate in this the conservation of energy for this problem. Okay, because the question's asking the energy that's given to the electron, and we should have enough to do it. So we know the energy of the initial photon. Okay, so the energy of that initial photon was 1.36 times 10 to the negative 17. That was given to us in the problem. The energy of the deflected photon, which is right here, well, we don't have that yet, but what we can do is we can find it. Because we know that the energy of the deflected photon is hc over lambda, and because we were able to find, or because we have everything we need to find it, we can simply go in and say hc over lambda, and we can do the calculation. We get 9.28 times 10 to the minus 19. And this is where this number then we're going to use in our formula. Okay? So then all we have left to find is the energy of the electron, and we simply subtract 9.28 times 10 to the negative 19 from both sides, and we end up with our result, 1.27 times 10 to the negative 17. So there's the energy that's been given to the electron. Finally, it says calculate the electron speed. We can say, well, that's going to be 1/2 mv squared. We rearrange that formula, and we come up with our answer. And of course, when we do this, we're hoping that our answer is not going to be above 3 times 10 to the 8th, because that's not possible. And we get, of course, 5.3 times 10 to the 6 meters per second, which is good. That's a good result. That's a good way for you to check your answers. If you find that you have an answer that is well above the speed of light, you've done something wrong, and you got to go back and check that out. All right, second half of this, Louis de Broglie, 1924. He's a French grad student, and he's working on Compton stuff, right? So he expanded on what Compton did. And he suggested that, hey, okay, photons have a detectable momentum, which is kind of a property of matter. Then maybe it's possible to explain matter in terms of waves, right? And so it was like, okay, well, the reversibility of, matter and waves, like particles and waves, that kind of reversibility is not a far stretch, because we've seen the reversibility of electricity and magnetism, and that really those two things are are just two sides of the same coin. So here's what de Broglie stated. He said he took Compton's equation and he said, okay, well, if P is equal to H over lambda, then lambda is equal to H over P. And if we're talking about matter, we're talking about things, then we could say lambda is equal to H over mv. And this became known as the de Broglie wavelength for particles. Now, this was a really, really radical idea, right? That we could have a particle and that it could exhibit wave-like properties. This is a really, really far out there idea. And so his graduate degree was held up for a year. They checked and they checked and they checked. But eventually, de Broglie was awarded the Nobel Prize in 1929 for his work because this was groundbreaking. So let's take a look at this in a couple of examples, and we'll see why this relates to the quantum world, but doesn't necessarily result to kind of the macroscopic world that we live in. It's not that it doesn't relate; it's that it's not noticeable. So let's find the de Broglie wavelength of a 1 gram steel bearing moving at 10 meters per second. So if you take a little steel sphere and it's 1 gram and you throw it across the room at 10 meters per second, would you see wave-like properties? And of course, we'll use the formula for the de Broglie wavelength. Lambda is equal to H over mv. Sub in our numbers, and we arrive at 6.626 times 10 to the minus 32 meters as a wavelength. So this is an unfathomably small wavelength that would not be detectable because this is so small. And this kind of starts to point us in the direction of why we don't experience quantum effects in the world that we live in on a day-to-day basis. Okay. However, when we start going smaller and smaller and smaller, find the de Broglie wavelength of an electron that's accelerated from rest through a potential difference of 50 volts. Now we say, okay, now maybe we're getting close. So we know that to find the de Broglie wavelength, we need mass and we need velocity. Well, we know the mass of an electron, but there it is. What's the velocity of this electron? This tells us it's accelerated from rest through a potential difference of 50 volt. Okay, hold on. There's something that we got to remember here. We got to remember conservation of energy from our fields unit. And we say, okay, well, the change in electric potential energy is going to equal the change in kinetic energy. And so when we multiply these things out, here it is, Q delta V equals 1/2 mv squared, and we sub in our numbers. Of course, an electron is charged negative, so those negatives will take care of themselves. We end up with 4.19 times 10 to the 6 meters per second as our velocity. We can sub these numbers now into the formula for the de Broglie wavelength, and we end up with 1.73 times 10 to the minus 10 meters, which is 0.173 nanometers. And this is, yes, this is a very small number. However, this is a result that is not unfathomably small anymore. So this is something that's pointing us in a direction. We've got a couple cool videos to show in class about this kind of stuff. All right, there you go.